Today's lecture will be in English. I will give a brief introduction of the talk of the lecturer. And after the lecture, you will be able to ask questions. So let's get started. The title of the lecture is The Unbearable Lightness of Neutrinos. Title may remind you of the famous novels and movies about the unbearable lightness of being. So it's quite impressive. So today's lecture will be about the elementary particle, neutrinos, which will be presented by Professor of Carnegie Mellon University, Dina Pardon. The existence of neutrinos was first assumed approximately 90 years ago by Pauli, and then it was discovered in 1955. Neutrinos are considered to be one of the components of dark matter, our universe. The role in the processes of interaction of particles is very important. That's why they've been studied for decades, although there are still many unresolved problems. Professor Dina Pardon will also give us a remote tour of a modern laboratory where the experimental studies of neutrinos are carried out. So now, briefly about Dina Pardon. She earned her PhD in 2011 in Carnegie Mellon University about neutrons. Then she switched her study to neutrinos and went to a postdoc position at the University of Washington. And then after this, she returned to Carnegie Mellon University in 2017. And now she's an associate professor of physics there. She received an early career award in 2021. So, dear Diana, welcome to Elias State University. And thank you very much for giving a lecture on this very interesting and important topic of physics. Please, you can start now.
All right. Thank you very much for your virtual hospitality. I'm sorry that I'm not able to see your university in person, but I'm very excited to tell you all a bit more about some of the outstanding mysteries of neutrinos. I know there's some range of physics backgrounds of people attending, so I wanted to start with just a very quick discussion of where this fits into a larger picture of particle physics. And I think there are a lot of very specific questions that we want to answer in particle physics, but they're all related to some extremely deep and fundamental general questions. What is matter made out of deep down? How does matter interact with other matter or with forces, and what holds matter together, and where did it come from? And if you break matter down to small levels, you're left with really tiny pieces that have somehow fundamentally shaped the universe, and it's hard to see immediately how that can have been. So, for example, if we take a glass of water and we zoom in, we find that there are lots of H2O molecules in the water. Then we zoom in on the oxygen piece of the H2O molecule, and we find an atom with a dense positive charge in the center and electrons flying around outside. We zoom in on that positive charge, we get a nucleus, and we zoom in on one of the protons or the neutrons, and we get this soup of quarks and antiquarks and gluons, and there's just all sorts of interesting things going on when you drill down to deep levels. One thing that we've figured out is that it appears there are four fundamental forces. We've found a way to tie two of them together, so maybe the three fundamental forces, but at the levels we usually work at, we've got electromagnetism, which affects all particles that have electric charge. We have a weak interaction, which is short range. It affects quarks, which make up protons and neutrons, and it affects leptons like electrons or neutrinos. We have a strong interaction, which is very short range, and this affects quarks and gluons. This is the thing that holds a proton together and that holds the nucleus together. And then sort of outside the particle physics picture is gravitation. So we haven't figured out how to unite that with our standard picture yet. So this is sort of a visualization of the standard model of particle physics, which is our framework for thinking about how things happen at the very most fundamental layers of matter. And here we've imagined the fundamental particles as stuffed soft toys for children. It's actually possible to buy these online. But the different colors classify all of the known particles into groups, right? In pink, we have the quarks. In green, we have the leptons, especially my favorites, the neutrinos over here. In blue, we have the force-carrying particles, and then there's the Higgs boson down here that was recently discovered. And we can write down a very simple expression for explaining how all of these things work together. It's so compact that it fits on a coffee mug, but there are still a lot of questions about where the properties come from and how to calculate some of these terms that are much harder to work with than they are to write down. And beyond that, we also know that something is missing. So this is a plot of where the matter and energy in the universe come from. And you can tell what fraction should be in each category based on measurements, detailed measurements of the sky. So we know that about a quarter of the universe is shaped by dark matter, and we don't know what that is. We know that 2/3 of the universe, 2/3 of the energy in the universe is something called dark energy, and we call it that because we don't know what it is either. Even when we're talking about this ordinary matter orange slice, about 5% of the known universe is what I just showed you in the standard model, we don't know why is there more matter than antimatter in the universe, which allows us to be here. The standard model has 19 free parameters, like the mass of the electron, for example. We don't know why they have the values that they do. All of this leads us to the conclusion that maybe we don't completely understand particle properties and dynamics. Maybe there's more work to do. And we find ourselves, like detectives, going around and looking for clues, trying to pin down strange behavior and figure out what's really going on. And that's part of what we're trying to do with the neutrino. So you heard a little bit a couple minutes ago about how the neutrino was proposed about 90 years ago, and I want to tell you a little bit more about this story. So this story goes back to the 1920s when scientists were studying different kinds of radioactive decay, and they had figured out that different types of radioactive decay gave off different types of particles with different energy ranges. And they knew about something called beta decay. I've drawn a cartoon of how physicists thought of beta decay in 1925. You have some radioactive nucleus. In this case, it's tritium, or hydrogen with 2 neutrons, and it decays to another nucleus, and in the process, it emits an electron. Now, this is a 2-body decay because it has 2 particles in the final state, the nucleus and the electron. And you can measure the mass difference between these 2 nuclei, and you know how much mass the electron should have. And so in every decay, because these masses are constant, in every decay, you expect to get all of the electrons should have the same energy for a given nucleus decaying to another nucleus. And maybe your detector isn't perfect, so maybe this line kind of broadens out into a Gaussian shape, but it should all be falling at 1 energy. The problem is that when you actually go and measure those energies, you don't get a straight line broadened by your detector resolution. You get a broad, continuous spectrum that goes all the way down to basically zero energy. It's hard. It was very hard in 1925 to figure out what could possibly account for this. And some scientists wanted to say that maybe energy is not conserved. Pauli had a better way. He said, maybe there is another particle that's emitted. Maybe this is a three-body decay. And maybe this particle is invisible to the detector, so that's why we don't see it. But because it's there, the energy is probabilistically divided between this new particle and the beta, and that's why you get a continuous spectrum that's always at a lower energy than you expect. This was a really successful idea. It saved the conservation of energy. It led to the first workable theories of how beta decay works. But Wolfgang Pauli famously felt very bad about it. He thought that as a theorist, this was a kind of a terrible crime to hypothesize something that could never be detected and never tested by experiment. He was really worried about this. But I'm glad to say that, as you heard earlier, the neutrino was detected about 25 years later. Pauli was still alive. He and the experimentalists sent champagne to each other. Everyone was very happy. Oh, we've gotten pretty good at detecting neutrinos. They're hard to detect. They're sometimes called ghost particles because they are so hard to detect. But this is just a collection of pictures of experiments over the years that have been successful in doing so. Because neutrinos are kind of ghostly, because they're hard to detect and to work with, they've inspired people outside of physics also. So this is a poem by the American author John Updike, who was inspired to write about neutrinos. I am going to fact check this poem because, of course, John Updike was not a physicist. So he writes that neutrinos are very small. So he is correct. They are fundamental particles, as near as we can tell. They're leptons at any reasonable energy range. They are tiny. You can approximate them as point-like. He writes that they have no charge. That is correct. They are electrically neutral. That's part of what makes them hard to detect. He writes that neutrinos do not interact at all. This is false, luckily, because otherwise we would never know that they existed. We wouldn't detect them and we wouldn't see their influence on beta decays, but they detect via the weak interaction. It's very rare, so maybe this is some poetic license. He's mostly right that to neutrinos, the Earth is just a silly ball and they simply pass through. In fact, there are neutrino experiments that use the Earth as shielding. They're looking for neutrinos coming up through the Earth because no other particles do that. All right, there's one other point where Updike is wrong. He writes that they have no mass. I want to give him a little bit of a pass on that because when he wrote this in 1960, physicists would have agreed with him, but now we know better. And the way that we know is from some of these neutrino experiments. So Super K in Japan and SNOW in Canada. These are about 25-year-old experiments that won the Nobel Prize a few years ago. And they discovered a quantum mechanics phenomenon called neutrino oscillation. And to give you just a very quick introduction to this, you start out with a source of neutrinos, the sun. The sun is a wonderful, very intense nuclear fusion reactor. And many of these reactions produce neutrinos. And then you set up your detector some distance away. 1 astronomical unit is pretty convenient. So you place your detector on the Earth, and there's some distance L between them. All right. So the sun is producing neutrinos. Let's imagine that it's in this moment, it's producing 6 electron neutrinos that are going to arrive at the detector on Earth. This drawing is obviously not to scale. And they're electron neutrinos because they're created in reactions that have that also produce electrons, and you have an electron flavor tag associated with them. There are also neutrinos that are associated with muons or with TAs. So we have these 6 electron neutrinos at the sun that we expect to be able to see in our detector, but we only detect 2. And you keep on watching and waiting, and you calculate how often the neutrinos are going to interact and what the distance is, because the number of neutrinos falls off, and you always get only 1/3 of the electron neutrinos that you expect. Well, it turns out if you make a measurement that's sensitive to all 3 flavors of neutrinos, also the muons and the taus, all 6 neutrinos are there. It's just that even though the neutrinos were created as electron neutrinos, you're measuring them as muon or tau neutrinos by the time they get to your detector. Now, we now understand this phenomenon well enough that there are pretty good Wikipedia articles about it. I stole this plot from one, and this shows if you create an electron neutrino and you let it travel, so this the x-axis is the distance of travel divided by the energy of the neutrino, then you have some probability that you detect it as an electron neutrino, that's in black, but you also have some probability that you detect it as a muon neutrino in blue or a tau neutrino in red, and depending on where you're looking, where you put your detector, it might be more likely to show up as a muon or a tau neutrino than it would as an electron neutrino. And you can see this kind of oscillatory pattern where the probabilities go back and forth. It turns out, after a lot of thought, you can only explain this if your 3 neutrino flavors are actually quantum mechanical combinations of the 3 mass states. So here we've got this chart that's where each color is one of 3 different mass states. And then it turns out that the electron neutrino is a particular mix of those mass states. It's got some amount of mass 1, some amount of mass 2, some small amount of mass 3, and the muon and tau neutrinos similarly. So in the sun, you create a neutrino in a particular flavor state, but as the neutrino travels, the way that it travels through space depends on the mass. So the fractions change as the neutrino travels, and you have something that isn't a pure electron neutrino anymore. And so after it's traveled, there's some probability that you detect it as a different type of flavor. This is where the quantum mechanics comes in, there's some chance that the measurement could reveal any of the flavors, as long as it's not in a perfect electron neutrino state. It only works if the 3 mass states are different, if you have 3 different mass values. So neutrinos can't all be 0 mass, as John Updike and previous theorists thought. But we've got this neutrino to-do list for understanding them better. And we've figured out that neutrinos do not have a mass of 0. So that's good. We have a lot of additional questions. And the one that I want to focus on for the rest of this talk is the absolute mass scale. So if the mass is not 0, what is it? This is what's unbearable to physicists like me, that we don't actually know the mass value of the neutrino, even though it's some fundamental particle. And we don't know why they are so incredibly light compared to other fundamental particles, because we know whatever those masses are, they're down here at the left end of this spectrum. All of the other particles are out here, at least 250,000 times more massive. Why is there such a big gap? Why do the neutrino flavors mix with each other so much? Quark flavors mix a lot less. And we don't even know if neutrinos are their own antiparticles, and that actually relates to the mass question. So we have this standard model. Neutrinos do not fit in cleanly, and there's a lot that we need to understand. So for the rest of this talk, I want to go into just a little bit more detail about the neutrino mass and ways that we can access it and why we care. I want to tell you about a particular experiment that's located in Germany, the Catron experiment, and explain how it works. I think it will be interesting to talk to you a little bit about the types of backgrounds that we have to deal with in Catron. And then I will share our most recent results, which I hope you'll find interesting. So for the mass scale, we have, this is just another way of writing this chart that you saw. So we have increasing mass on the vertical axis. And we know the splittings, we know the differences between the mass values from oscillation experiments, but they can't tell us what the scale is. So we know there's this break in the y-axis. There's some offset of the lightest mass from zero. We don't know what that offset is, and that's what we want to try to find out here. One reason why this is interesting, apart from filling in a gap in our understanding, is that neutrinos may be really light, but they were also the most abundant matter particle in the early universe. I should say the most abundant known matter particle, right? I mean, there's some dark matter that we don't know about, but collectively, neutrino mass affected the way that large-scale structures formed. So this is a simulation from a while ago that's sort of showing it's a simulation of structures forming in the early universe, and depending on the sum of the neutrino masses, you can get a fuzzier set of structures or a less fuzzy set of structures. You can see this signature of neutrino mass. They're sort of cosmic archetypes. And that signature of neutrino mass, it's imprinted on cosmological data. If you count galaxy clusters, if you measure the cosmic microwave background, you should be able to see some signature of the neutrino mass. And almost uniquely among things we can measure in cosmology, you can also directly test it in the laboratory. So that's extremely exciting to be able to get this laboratory input to the way that the universe formed. The best laboratory way to measure this is actually through beta decay, the same process that revealed the existence of the neutrino. So here we're working specifically with tritium decay, hydrogen-3, and this is what we call in nuclear physics a super allowed decay, which basically means calculating the nuclear physics of this radioactivity is simple. So we like that. It's got a half-life of about 12 years. It's got a relatively low energy. And the basic idea is that the neutrino mass signature shows up in the very high energy tail if you measure the energy spectrum of the betas that are produced in the decay, these electrons. And that's because the mass of the neutrino is a packet of energy that the beta cannot carry away. So if you look at situations at the very high energy tail where the beta is taking away almost all of the kinetic energy, then the existence of a non-zero neutrino mass, shown here in red, is going to shift the spectrum a little bit to lower energies, and it's going to change the shape. And so the way that you do this measurement is to measure the spectral shape near the endpoint and compare it to the way that a neutrino mass would distort the shape. And then you can extract that mass. And this is the exact observable that we get. It's this sort of incoherent sum of the squared mass values weighted by their contributions to the electron flavor state that is created in the decay, because you've got some admixture of the mass values. And then that gives you a squared effective mass. So this is all very straightforward. The theory is very straightforward. It seems like it should be simple. You just make a shape measurement and then you publish. It turns out that there are a few challenges. One very big challenge is that if we want to go from the whole spectrum of all the tritium that is decaying to the region that carries useful information about the neutrino mass, we are looking at a very tiny fraction of the decays that carry useful information. 1 part in 10 to the 13 decays fall into this last range of the electron spectrum. So the first thing is that you need to have a huge number of tritium atoms decaying so that you can actually observe some decays happening in the useful region. You need to very precisely measure the energy and the rate near the endpoint so that you can get this, this shape out. And you need to do that without being completely swamped by all of the low energy decays that don't have any useful information about the neutrino mass. Now, that's the challenge that the Catron experiment has been trying to solve. And that's what I want to tell you about next. Our trick is called a MAC-E filter, which stands for magnetic adiabatic collimation with an electrostatic filter. And the basic idea is very classical. We allow the tritium to decay in a strong magnetic field. And then we move, we guide the beta electrons out on magnetic field lines, and we move them from a region of strong field at the left to a region of weak field in the middle. And if we do it gradually enough, then the magnetic moment mu in this equation is conserved. It's a constant of the motion. And the magnetic moment is just a ratio of the kinetic energy due to motion perpendicular to the magnetic field divided by the strength of the magnetic field. So as you move from a region of strong field to a region of weak field, you gradually line up the electron momentum. You rotate the electron momenta so that they're almost parallel to the field lines in this central region, right? Because as the magnetic field gets smaller, the kinetic energy transverse to the magnetic field also has to get smaller. And so you end up with a very, very broad, loosely collimated beam. And once you do that, you can apply an electric field going the opposite direction, right? So this electric field is slowing down the electrons. And because all of the electrons are moving kind of parallel to the electric field, it sets a threshold on the total kinetic energy. So electrons above that energy can pass through and be detected. Electrons below that energy bounce back toward the source, and they never get detected. So this basically works like, if you know about electronics, it works like an integrating high-pass filter. You are counting up all of the electrons above a certain threshold, and then you can map out the shape by shifting the threshold. And your precision in doing this, the width of your filter, depends on the ratio of the minimum and the maximum magnetic fields. So to go into just a little bit more detail about how this works, you end up with some transmission function like this, right? So below this energy, none of the electrons get through. Above this energy, all of the electrons get through. And in between, there's some slope as more and more electrons get through, just depending on how good a job we did at lining them up. So we set the potential, we record the rate of electrons at the detector, and then we map out the spectrum by increasing the potential and recording at each step. So we have here just a plot of how this works if you're looking for at an electron distribution with just one energy. So we have this calibration source that produces electrons that follow this line shape. And if you measured this with a Catron filter, then you end up, if the threshold is down here at low energy, you're seeing this entire line. So your rate is very high. As you increase the threshold, you remove more and more of the low energy tail until here you're crossing the bulk of the line and the rate is falling off very fast. And then out here, your threshold energy is too high. You're not really seeing anything from this calibration source. And so you have a very low rate. So this is just to show that, kind of the shape of the spectrum that you get is a little bit different because of this integration, but you still have all the information that you need. In order to make this happen, there are some technical challenges to be solved. So in Katrin, we have a beamline that's about 70 meters long. I'll show you the scale for a person very soon. But we have a gaseous source where our beta decays happen. We have our tritium there. We have upstream of it, we have some calibration to help us understand what's happening. We've got a section where we're trying to hold the tritium back while we transport the electrons forward. And then we have a set of two Mackey filters, two spectrometers that allow us to analyze the beta energy and get this integrated population that survives to the detectors. And to make all of this good enough to really get information about the neutrino mass, right, the design goal for Katrin is 0.2 electron volts. In particle physics, we ignore factors of C, and we just say this is it's the same as 0.2 EV over C squared. We want to get a sensitivity down to a fifth of the energy that it would take an electron to climb a 1 volt barrier. And to do that, you would need a magnetic field range between 3 Gauss and 60,000 Gauss. You need 10 to the 11 decays in the source every second. You need a source that's where 95% of the atoms are tritium. And your main spectrometer, the big Mackey filter that's sorting out the electron energies relative to a threshold, you need a volume of more than 1,200 cubic meters. In real life, that is a lot. So you can see here, this is our main spectrometer traveling through the village outside the laboratory. So this was right before we were able to put it in the experimental hall. You can see if we wanted to build a bigger experiment, we would not only need to improve our vacuum technology, but also our village technology so that it would fit. Even when we have it in the experimental hall, there's a big challenge. So this is one of my colleagues who has, we had teams working for years to line the inside of the vessel with wire electrodes to shape the electric field inside. When we were ready to close it up, this is a pump port for maintaining a good vacuum. And you have to lever up this flange that's 2 meters wide and then fasten all of these bolts around the external ring. So even, just getting this thing up and running is a huge challenge. But once it's running, there are more challenges to do. I wanted to show you one of them because I think it's interesting. Background is something that appears in our detector and seems like it might be the thing that we're interested in, which is a beta electron from tritium beta decay. But actually, it's an electron or something that came from somewhere else and is only disguised as what we're interested in. We call this a background because it makes it a little harder to see the picture that we're looking at. A lot of sensitive particle physics experiments have to worry a lot about backgrounds, and sometimes they can be pretty weird. That's what I want to show you now. Our basic problem in Katrin is the way that our measurement is designed, right? We have beta electrons, we get their momentum lined up in the middle, and then we slow them down almost to zero velocity before speeding them up again. So they have very little kinetic energy in this central region. And that means if you accidentally make some electrons with really low energy in the middle, then they are also going to be reaccelerated onto the detector, and they're going to be indistinguishable from the signal, or they're going to have very close to the same energy as the signal. I want to explain to you one way, one of the main ways that happens in our experiment, but I want to give you a feeling first for the type of complicated story that I'm going to tell. So this is a cartoonist from about 100 years ago, Rube Goldberg, who built his whole career out of designing ridiculously complicated machines to solve simple problems. So in this case, this gentleman is eating some soup and he wants a machine to automatically wipe his face with a napkin once he has eaten the soup out of his spoon. In order to accomplish this, the spoon is connected to us by a string to this catapult, which flings a cracker into the air. The parrot leaps up to get the cracker. That removes the counterweight over here, so you end up lighting the fuse on this rocket, which cuts another string, which allows the pendulum to swing and wipe his napkin. This is a ridiculous way to solve the problem, but this is the type of multi-step process that leads us to our biggest background. So what happened is that our spectrometer is partly in the basement of the experimental hall. And one thing that often happens in basements is that there's some radioactive gas called radon that comes out of the rock and circulates in the air and gives off some radioactivity. So we had some radon in the basement, and some of it decayed into polonium-214, which kind of stuck to the wall, the steel wall on the inside of the main spectrometer. Then the polonium-214 decays. It decays via the alpha process, which gives it a kick. And so the daughter from this decay, lead-210, is implanted just inside the wall, just maybe a couple of layers of atoms deep, but enough. It sits there in the wall. And over time, it decays. So the decay chain over time takes us to the next isotope that we care about, which is polonium-210. Polonium-210 is another alpha decaying particle. So it gets a kick. And then either either the daughter nucleus or the alpha particle can end up coming back out to the surface of the stainless steel. And on the way, it knocks off other atoms from the surface. There's hydrogen trapped on the surface of steel. There's chromium, there's iron, there's all sorts of stuff. And when these atoms are kicked off the surface in the aftermath of this decay, they're often really, really excited. So they're neutral. They pass right through our wire electrodes. They can enter the magnetic flux that's transporting our particles. We've got countermeasures against charged particles making it through, but neutral particles are fine. But then they're so excited. They've got the electrons. The electrons aren't tight in, like in the ground state of an atom. They are far out. They are so lightly bound to the nucleus that they can be ionized by the black body radiation that our room temperature spectrometer is just always giving off. So you've got these low energy photons that come in and just knock this lightly bound electron off. It's got almost no energy, and it gets reaccelerated just like the signal electrons, and ends up straight in our detector. When we first came up with this scheme, we thought it was far too complicated and must be wrong, but it's consistent with all of the data that we've taken. And we've actually tested it. We used a different isotope of radon where all the daughters are really short-lived, so we wouldn't contaminate our equipment for a long time. And this is our main source of background. There's not a lot that we can do about it directly, right? Because the lead-210 is just embedded in the steel walls. So one thing that we can do is that we can take advantage of the fact that this background sort of depends on the volume that the detector is seeing, right? So our neutral atoms are escaping out into the volume of the main spectrometer, and they're just randomly diffusing around before they get struck by a black body photon and they're ionized. So if you can make the volume smaller, then you can reduce the background. And so we do that now. We have a more complicated magnetic field setup where instead of being slowed to zero In the middle, the electrons are getting their minimum energy down very close to the detector, and that squeezes the envelope that they're traveling in so that it reduces the volume. The energy, our ability to measure the energy precisely is a little bit worse. We have to work harder on the analysis because the fields are more complicated, but it reduces our background by about a factor of 3. So that's very exciting. And we're working on a few other ideas. There's one other interesting background source, which I think I will skip for the moment in the interest of time, but please feel free to ask about it, because I want to make sure to tell you what we found out about the neutrino mass. So the basic idea here, I want to talk a little bit more about the shape of the spectrum that you measure, right? So this in dark blue, this is if the neutrino doesn't have mass. And then this dotted line, that's if the neutrino has a relatively large mass of 2 eV. And we have just these data points that give us this is a simulated measurement. This is a toy measurement for trying things out. And we can describe the shape with 4 parameters. So there's, there's some overall amplitude or intensity, which essentially tells us how much tritium we have in the source, right? That just increases our rate or decreases it depending on the amount of tritium. We have a background rate, which is hopefully small, and we treat that as kind of just some flat floor that the tritium spectrum is sitting on. So we can raise or lower the floor, and then the amplitude tells us the size of the tritium spectrum that's sitting on top of the background. Then there's a spectral endpoint. For various technical reasons, we'd actually we don't know the mass difference that precisely. So we don't know exactly where the tritium spectrum stops. And so we have this parameter that tells us where the tritium contribution stops. And then we have this shape parameter that the neutrino mass kind of makes the spectrum more or less curved. So kind of 4 free parameters in the fit in order to describe the spectral shape that we measured. So we took some data. This is our first data set from 2019. We enlarge the error bars by a factor of 50 so that you could see them. We take a modeled spectrum and simulated spectrum, and we fit it to the data that we measure. We treat the whole detector like one thing. We combine, we have a lot of different runs, and we combine the corresponding points between all of them. We have different teams with different fitting software cross-checking against each other to make sure that we didn't do anything wrong. And we figured that the neutrino mass, based on our first data set, is less than 1.1 electron volts. And we are statistically rigorously confident at 90% that it is definitely less than 1 electron volt. We kept measuring, and when we combined our first 2 data sets with spectra very much like that, we could bring it down even further. So 90% confident that we're below 0.8 electron volts. And we've kept on measuring. So this is a plot that shows how many total electrons we've been producing that are in the region that we measure. And so you can see it going up and up over time. The colored bands are the times when we were actively taking data. You do have to shut down for maintenance sometimes. So this green band, that's our first data set. The kind of bluish purple band is our second data set, where we could combine those two to get a limit below 0.8 electron volts. In red, that's when we tested our new run mode to reduce the background further by shifting the analyzing plane. And then red, yellow, and purple, we are finalizing that analysis. We are preparing the results now and working on a paper, so please stay tuned. And then, of course, after that, we need to focus on green and red. And actually, we just finished yesterday an 8th measurement time to measure the neutrino. We're very proud that we were able to safely keep running during the pandemic. So these are 3 of my friends of colleagues demonstrating how they could keep far apart from each other on a shift. And we've been very busy even apart from the measurements. So we've got new calibration data that we're using to better understand our equipment. We've got new ways of thinking about the uncertainties in our measurement. How do we know that that is the energy? How do we know how often the electron scatters and loses energy before it makes it to our filter? And we've been working on searches for even stranger physics, right? We know that the neutrino has some mass. We don't know what that is. But there are other weirder things where we don't know if it happens or not, but we can look for it in our data. And that's been fun too. So I wanted to finish up with some time for questions, but first I want to give credit to the incredible group of people working on the neutrino mass measurement. It's about 150 people around the world. And I think actually my slide was out of date. I left off a couple of institutions, but we work hard. We have a lot of fun. So I hope that I've persuaded you that neutrinos are really weird. They're very, very strange, but they tell us a lot of interesting things. And we've learned a lot about neutrino mass to help inform a lot of different questions. So our direct limit is now, we know that the neutrino weighs less than an electron volt from direct laboratory work. This plot here, this just shows the laboratory neutrino mass values from the 1990s all the way to today. And you can see by the way the error bars have shrunk that we really have learned a lot. The Katrin experiment is up and running. We've got lots of data on disk. We're taking more. We've got better control of our uncertainties. We're going to run for a couple more years and hopefully find out a lot. So I want to thank you for your attention and your virtual hospitality. And I'm eager to answer any questions that you might have.
Thank you so much, Diane. Yes, so let's see if any students are not shy to ask the question, maybe from the online or in the in the room. Maya?
Thank you very much. This very, very interesting presentation, lecture. Well, are there any questions? Yes, please.
Hello. Thank you for the presentation. It was very interesting. My question, I have two questions. First, you said, okay, the mass might be, is like less than 1.1 electron volts, but this is not the exact mass, right? Like we know the exact mass of the electron or proton. So how long is it left to like actually find the mass and like that's your main plan, right? To actually measure
Yeah.
right? And also, which programming languages would you recommend like learning if you want to analyze the data or like the databases?
Okay.
That kind of facility. Thank you.
So thank you for those two great questions. One of them is a very big question and one of them is a very practical question. So first, the kind of the bigger question, you are absolutely right. We want to measure the neutrino mass. We want to measure a neutrino mass that is where we know like there's some error bar on both sides, but we can say, this is where it lies. We can't do that yet, right? So there's some range of possible mass values that's kind of allowed from what we know about the mass splittings, but there's a lot of range there. So I think the lowest effective neutrino mass could be down to about 0.04 EV. So we're exploring all of that space that's available in the laboratory. Right now, it looks like so far, according to the data that we've analyzed, the neutrino mass is smaller than what Katrin can measure. And we hope that as we get more statistics, as we get more and more events that we're looking at, and we get better control over our other uncertainties, that we'll have the sensitivity that's required to measure the neutrino mass, but we don't know what that mass is. So it might be, I hope not, but it might be that neutrino the neutrino mass is not measured by Catrin, and that Catrin can only set limits because there's only so far down that our experiment can go. And in that case, you would need new and different ideas to try to push that sensitivity to be even greater, so that you can be sensitive to masses that are even smaller. And there are a lot of people who are working on research and development for ideas like that in the laboratory. It's very exciting. But yes, so we don't know where the mass is, and we're just sort of peeling back layers of the possible space where it could be to try to get at it. I hope that answers the big question, the first question that you asked.
Yes. Yes.
All right, good. And then for the practical question, so for programming languages that we use in analyzing the data, there are sort of two main languages. So there's C++. We do a lot in C++. It's very efficient, right? It allows you to do operations in a small amount of time. And we need to do a lot of operations. So for many parts of our analysis, this computational efficiency is important. We also use a lot of Python because Python has many advantages, some very powerful libraries that are available, not quite as computationally efficient as C++, but very good. In particle and nuclear physics, there are other programming languages that we use called, some things we've used in this experiment are Root for data analysis, Geant4 and Cassiopeia for simulation, which you may not have heard of. Those are all built on top of C++. So it's sort of like learning a new C++ library in order to use those. But basically, it comes down to C++ and Python.
If no other question, I can ask, right? Probably. Yeah. So first, thank you very much for this wonderful presentation. And as far as I know, one of my former students thanked you. So she has worked on the theory side. So could you please comment, is it possible that this neutrino mass is not constant while the universe is evolving? So as far as I know, there is this mass varying neutrinos model by Pardon, and one of the authorities, Weiner from New York University. Mm-hmm. Is it possible that what we are measuring basically in the lab, it is today value, but in the earlier epoch, it might be like 0, and during some kind of the phase transition, neutrino gets the mass?
Yeah, so that's a really interesting question. Thank you very much. And I am going to back up a little bit to give a little bit more context. First, I want to say, of course, I mentioned how in the lab we can measure this number, or we can try to measure the neutrino mass that goes into cosmology. Cosmologists also work on measuring the neutrino mass because they have all of this beautiful data about structure formation in the universe. And so far, they've set very tight limits, actually tighter than Catrin, but also haven't found a neutrino mass. And so something very interesting would happen if Catrin measured a relatively large neutrino mass value, and the cosmological data were saying, no, the neutrino mass is very small. Then this is exactly why you want to test things in a laboratory, because it shows that something is wrong, or it would show that something would be wrong about our assumptions, right? That these numbers are not quite comparable. And maybe it tells you that there's something, that the cosmological standard model isn't the correct description of what was happening in the early universe. Or, and this is what the question is about, maybe it tells you that that there's something different about particle physics that would also change your assumptions. So this idea of mass varying neutrinos, I think the mechanism that I'm most familiar with. So the idea is that sort of over time, the effective mass of the neutrinos has changed. So it's not a constant input to the standard model, but something that changes over time. So maybe when structures were forming in the early universe, it was very small, but then by now it's relatively large, and your lab measurement wouldn't be consistent with the cosmology measurement because they're at different times. And the mechanism that I've seen to kind of propose this idea is that maybe this, the variation of the mass would depend on the density of matter around the neutrinos, right? And the early universe is really, really dense compared to now. And so that would have reduced the effective mass. I think it's an interesting idea. And if we end up with a mismatch or a disagreement between cosmological measurements and neutrino mass measurements, then that could be evidence of that idea. There are a lot of other possibilities that could explain it. I've thought a little bit with a few colleagues about how you might test whether this mass varying neutrinos idea is correct. It's really hard to think about how you would test that that's what's happening as opposed to another idea for explaining the discrepancy. The one idea that we came up with, which would be really hard for different reasons, is supernovas, because when a supernova, when a core collapse supernova happens, you have the core of the star that's collapsing, and it is very, very dense, and neutrinos are escaping through this very dense matter. So if dense matter means a lighter neutrino, then those neutrinos created at that moment would have a smaller mass. And you can, in principle, you can try to measure the neutrino mass from a supernova explosion by looking at when the neutrinos arrive at your detectors based on their energy, that the dispersion should give you the mass. And maybe that would give you some insight into whether the neutrino mass from the supernovae was different from the neutrino mass in the lab. But there's also a lot that we don't know about supernova dynamics, so I don't know if we could get the sensitivity that's needed. So I think it's a really interesting question that's fun to think about.
Thank you so much. And one, I mean, it is not related to the mass of the neutrinos, but the question, as you are expert on the neutrino physics. So we know that through the electromagnetic radiation, we cannot see the earliest epoch than the cosmic microwave background radiation formed. So before this gravitational waves detection happened, there was a discussions about the option for the observing the early universe through the neutrinos, just like cosmological background of the neutrinos. Do you think that it is something promising way, or it's absolutely not possible? I mean, it's very hard, I understand, but maybe it was the same thoughts about the gravitational waves, but we detected them. So any comments about the cosmological neutrinos background?
Sure. So I think my first comment would be that basically every neutrino experimentalist has dreamed about measuring the cosmic neutrino background. Because it's very exciting. These would be neutrinos produced 1 second after the Big Bang. This would be fantastic for so many different reasons. What makes it so challenging is, of course, the cosmic microwave background. You can see how the photons have a very low energy, right? Because the expansion of the universe has cooled them effectively. And the same thing happens to these relic neutrinos from 1 second after the Big Bang. So we are talking about almost no energy, almost no kinetic energy in the neutrinos. And that means that most of the good ideas that we have for measuring neutrinos, so if I'm not sure if there's a great way to skip back, but I will try. So I showed you all of these I showed you many different neutrino detectors, and all of them they measure neutrinos from neutrino interactions that kick in above some certain energy. So that would not be available, or those detection methods are not available for cosmic neutrinos because they don't have enough energy. So the one idea, right, so all of these beautiful detectors are not going to work because the energies are too low. So the one idea that people have suggested is actually, I'm going to use this plot. So there's one reaction that can happen to a neutrino with almost no energy, which is that it can capture on a nucleus that already beta decays. It can basically stimulate a beta decay, right? It's a little bit different because here the neutrino is coming in, so it's in the initial state, but it's not in the final state. And the experimental signature, if you look at this beta spectrum, the experimental signature would be that you would get a little bump of betas above the natural energy maximum of the decay. And it would be above the natural energy maximum by units of 2 neutrino masses. So it would be separated from the regular spectrum by a very small amount because the neutrino mass is very small, but it would give you that signature. So we've actually looked for that in Catrin. We're not very sensitive to it in Catrin. So there are predictions for how many of these cosmic relic neutrinos there should be per cubic centimeter. It's about 300 per cubic centimeter. So they're pretty dense. But we're sensitive to situations in which you have more like 300 million cosmic neutrinos per cubic centimeter. And there are some theories where you could get local big densities of relic neutrinos, but so we're basically just testing those. It's very hard to get past that with an integrating measurement because you're less sensitive to these little bumps. There are some experimental ideas. There's a Ptolemy collaboration that's trying to measure this. I think I don't give them high odds of success, but I think that they're doing some very interesting work in identifying some of the problems involved.
Thank you so much, Diane, for this wonderful talk. And again, so we can talk more later on, maybe something merging cosmology with particle physics will end up with a nice model for the mass of the neutrinos. And again, thank you very much for agreeing to give this talk.
It was my pleasure. Thank you so much for inviting me.
Yeah.
Thank you very much. Any questions? There are any questions?
Okay.
Just one.
So we will post this one in the university webpage when the video will be redacted in some sense, and we will give you also the link just to, just have this video recording as well. Okay.
Okay. So we have one question.
It was very interesting to hear you talking about neutrinos. And my question is about, yes, it is interesting to find out the mass of neutrinos, but does it have any practical usage? When we find that mass, what we will do after with it? Like what will be what will happen after that?
Sure. So that's a good question, right? Like, what does this tell us? Does it allow us to just fill in a missing number in a table, or does it have some deeper meaning? And the short answer is it turns out. So we've got this beautiful standard model. Neutrino mass is not in the standard model. The standard model assumes that neutrinos are massless, and you actually, for technical reasons, you can't give neutrinos mass in the same way that you give electrons mass or quarks mass. There are a lot of different ideas for how you can extend the standard model to put the neutrino mass in, but to try to see which of these theoretical ideas is right, it's really helpful to know what the mass actually is. And some of those theoretical ideas have consequences. So for example, I mentioned that we don't understand why there is more matter than antimatter in the universe. We're very grateful for it. It allows us to exist, but we don't understand why. Some of the models for explaining neutrino mass could also help explain why there is more matter than antimatter in the universe. But to get there, we need to know what the mass value is. So scientifically, it's a very fundamental issue for theory, for cosmology, and for understanding some other neutrino properties. Practically speaking, and for detecting the relic neutrinos that we were just discussing, you would also want to know how much resolution do you need to resolve that other extra peak. Practically speaking, in terms of improving, daily life, probably not much application, but it would make a lot of neutrino physicists happy.
Thank you very much.
Yes, and thank you for Maya for mediating this meeting, and also for all people who were organizing it. Thank you so much, everyone.
Thank you from my side too.
Yeah,
Okay.
there are some. I'm looking for if there are any more questions in chat, for example. Well, there are thanks. Thank you very much. Thank you. Welcome. I don't see any questions in the chat. Just thanks.
Okay. Thank you. Thank you, everyone.
If there are no questions, then I would like to thank Diana a lot for this very interesting, wonderful presentation. Yeah, I think we got quite a lot of knowledge from this lecture, right? Yeah, they agree with me. So, thank you very much, and I hope to meet again sometime.
Maybe in Georgia.
Yeah,
Right.
yeah, in Georgia. So, if anybody wants anything to say, no.
Yeah.
So
have everyone wonderful day, right?
thank you.
Bye-bye.
All right. Thank you very much.
Thank you. Thanks a lot.